Hey, what's up YouTube? It's BetaPlayer1011 here, and today we'll be talking about limits. More specifically, limits of polynomials, or fractions, where there's a polynomial in the numerator and a polynomial in the denominator, and what their behavior is as the limit of x approaches infinity for this f of x function that I've written on the top. Now, the thing we have to remember is what the limit as x approaches infinity of 1 over x is. And this is a very easy limit to think about because let's say x is 10. 1 over 10 is 0.1. Let's say x is 100. 1 over 100 is 0.01. 1 over 1,000, 0.001. And as you keep getting bigger and bigger, the numbers that you evaluate get smaller and smaller. Soon, you'll reach a point where it's infinitely large, and the limit as x approaches infinity, the entire function approaches 0. And this is very helpful because this means that when we have polynomial functions, or in the numerator and denominator, we can divide by the highest power of x and simplify a lot of things to 0. Now, let's do this first example here. So this says that p of x is greater than q of x. So let's use an example. What I mean by that, when a polynomial is greater than another, I mean that the highest power of the numerator is greater than the highest power of the denominator. So I'm just going to make up a random polynomial here. And since p of x is greater, I'm going to have a lower power in the denominator, x squared, plus, let's say, 5x minus 10. So what we're going to do is we're going to divide by the highest power, x cubed. So we're going to end up with x cubed divided by x cubed plus 2x squared divided by x cubed. Then we have minus x over x cubed. And then we add 5 over x cubed. And that's the numerator. In the denominator, we have x squared over x cubed plus 5x over x cubed minus 10 over x cubed. Now, what we're going to do here is this will go to 1. So this will be 1. This x squared over x cubed simplifies to basically the form of 1 over x. So this will go to 0. This will also go to 0. This is basically 1 over x squared. And this is 1 over x cubed. As it approaches infinity, this will approach 0. Now in the denominator, things work a little bit differently. We're going to make things a bit simpler and also simplify these two to 0. But we don't want to get rid of all of our x's. So we're going to leave the numerator because all we want is a general statement. And the numerator will have the highest power will have the biggest effect. So this will simplify to 1 over x. So what we end up with the general form for when p of x is greater than q of x, we end up with 1 over the fraction 1 over x. And that is simply just x. And if we have x, y equals x as it approaches infinity, the entire function approaches infinity. So what we end up with is the statement, when p of x is greater than q of x, then the limit as, I'm going to write this out fully, as x approaches infinity of p of x over q of x Sorry about that. Over q of x is equal to infinity. Now let's do the second one. The second one is down here. If q of x is greater than p of x. So let's switch this around. We have x squared plus 5x minus 10 all over, now we have x cubed plus 2x squared, looks messy, I'm sorry, minus x plus 5. So we're going to do the same process. We're going to divide every term in here by the highest power being x cubed. So we end up with x squared over x cubed is going to be 1 over x. Now every term after this will be as such. We have 5x over x cubed, that's going to go to 0. As you can see, the point here is that we just get rid of all these extra terms. So this will go to 0, just as we did above. Minus 10 over, this should be a plus, x cubed. And this will go to 0. All over x cubed over x cubed is just going to go to 1. Sorry. So plus 2x squared over x cubed, that's going to go to 0. And then plus 5, or minus x, sorry. So minus x over x cubed, that's also going to go to 0. And I think you get the point from here on simplifying every term after this to 0. So 5 over x cubed, it's also going to go to 0. So we end up with this 1 over x all over 1, which is 1 over x. And this is because we have 1 over x here, 0, 0, over x cubed, which is just 1, and then 0, 0, 0. And this limit is the same thing as here, so the limit as x approaches infinity is 0. So for this statement here, and I'm going to put it in this box over here, when q of x is greater than p of x, the limit, I apologize for it being sloppy, as x approaches infinity of p of x over q of x is equal to 0. Alright, and now the last thing is when they are equal, and again, this will just be the exact same process, but let's erase this on the top so I have enough room. You can go back in the video if you missed any of it. And, alright, let's do this in a different color, in green. So let's bring that up over here. So let's say we have x squared, let's put a 5 in front of it, plus 5x, minus 10, all over, let's put 2x cubed, x squared, my bad, plus x minus 5. So we're going to do the same process. We're going to divide everything by x squared. And what we end up with is, let's see, 5x squared over x squared is just 5. Now, 5x over x squared, that goes to 0, again, because 1 over x as an approach to infinity is 0. We're going to have 0. And then 10 over x squared, again, that also approaches 0. It's the same process we did down here. Now at the bottom, 2x squared over x squared is just 2. And then we add 0 and subtract 0 again because x over x squared goes to 0. Minus 5 over x squared, that also goes to 0. And we end up with the limit is 5 over 2. And that's going to be the horizontal asymptote for this. So I'm going to draw a graph after this and show you. But basically what this says is that when q of x is equal to p of x, or it should be p of x equal to q of x, but they mean the same thing. When q of x is equal to p of x, the limit as x approaches infinity of p of x over q of x is equal to a over b. And a over b are the coefficients of the highest power. So as you can see here, 5 over 2 is just this. So you go to the highest power, and you take the coefficients, and that is your answer. 5 over 2, 5 over 2. Now let's analyze what the horizontal asymptotes are before I go into the last topic. So the last two examples I gave had horizontal asymptotes, meaning that as they approached infinity, they approached a certain number that was not infinity. So for the example of the second example, where it's q of x is greater than p of x, what we had was, let's draw this graph here. Let's draw two graphs actually. What we basically had was this. As it approached infinity, we approached 0. So as you can see, this is a horizontal asymptote over here. It never crosses 0, but it approaches 0. On the second graph, where we have q of x is equal to p of x, here, let's draw this line. Let's say this is where the line 5 over 2 is. What this graph will look like is something like this, where as it approaches infinity, it approaches 5 over 2. That is the horizontal asymptote. And one last thing before we finish this video is the vertical asymptotes. So since it's in a fraction form, what we know is that, well actually there are two more things I want to cover. Yeah, so what we know is that when it's in a fraction form, the denominator q of x can never equal 0. So I'm going to put q is never equal to 0. So the way you find the point where you have a vertical asymptote such as this is when q is equal to 0. Because when you have 1 over 0 or any number over 0 where 0 is in the denominator, the limit it's undefined. It doesn't exist. So 1 over x, let's say it's 1 over 0. That's why the graph of 1 over x is a vertical asymptote at 0, because x at the bottom is equal to 0. So whenever you want to find the vertical asymptotes, always set q of x equal to 0. Anyway. Now I believe there's one more thing. And that is finding the limits when it's not approaching infinity. And what you can do to make sure that the limit doesn't exist, or when you want to find the limit, not necessarily that the number, but here, let me explain myself in a better way. Sometimes when you plug it in directly into the equation, what you find is that, sorry, not eraser, pencil. I'm gonna use a line for this. What you find is that, when you plug in the numbers directly, you get an undefined answer. However, sometimes that isn't correct for the limit, because the limit is as it approaches that number, not that number specifically. So let's take this example here. Whoops. Let's take this example here where this line goes up like this, and then down like this. Let's say this is at 2. So when you plug in 2, you're not going to get a defined answer, but as you approach the number, the limit definitely exists. When you come from the left and the right, you end up at the same number. Let's call it y. So the limit exists, but it's undefined at that point. Remember, the limit is as you approach that number from the left and from the right, and you approach the same number, then the limit exists. At 2, it's undefined. So let's take an example where it's in fraction form, where you have x squared minus 4 over x minus 2. And I want to know what the limit is as x approaches 2. So when you plug it in directly, what you'll get is that you have 4 minus 4 over 2 minus 2. You're going to get an indeterminate number, but you just plug it 2 minus 2 is 0. So normally we'd say obviously it doesn't exist there. However, what we can do is we can simplify this. X squared minus 4 factors into x plus 2 and x minus 2. And then as you can see in the denominator, we have an x minus 2. So we have x minus 2. So what we can do is we can simplify it by canceling these two terms out. And we end up with the x plus 2. So as it approaches 2, plug it in. 2 plus 2 is 4. And that's your limit for that question. I hope you enjoyed this video. If you enjoyed it, give it, or if you learned something, give it a thumbs up and subscribe. And I'll catch you tomorrow with another lesson. And today, later, with a discussion on the recent police shootings.